One thing that we can do at a more advanced level in Java and in many other languages is to write programs that change our programs or change our classes or change features about objects. When we do this sort of programs that mess with the inner workings of programs, it's called reflection. And in Java, there's a special library that we can import that allows us to do this reflection work, Java lang reflect, and it has many classes and components built into it. So what you'll see in the example here is that we've got three classes that we've written. Class A, which just has a course string variable that's public and contains CS. Class B extends A, meaning that it inherits that course string variable, and it has more variables of its own that are private, an integer for the number, the course number, and an integer for the year. It has a couple of methods. One of them is a toString that just combines the course number and the course name, the course number, and the year. And another one that returns us a B object. It's a static method, so it belongs to the class B, not to instances of B, not to actual objects of type B. And then we have this reflection class that we are writing. This is not a Java or a built-in Java class. This is something we're writing to mess around a little with reflection. It's got a method that will double a string. If you give it a string, it takes that string and gives it back double, twice its contents. And then it's got this basically empty void method here, just called SumMethod. Then we write a main method that's going to do some reflection in it. We will notice that it just throws generally exception because this sort of stuff that we are doing with reflection can lead to tons of different kinds of exceptions. We're often playing pretty fast and loose with the inner workings of classes here. So for instance, we get an object variable and we just have B generate us a B object. That will give us one with all those basic variables, the string for the course, and then the number and the year. And it will be able to use its methods if we can get Java to treat it as a B, because you notice that we created it as an object variable. We then can create a variable of type class. This is where it will get a little weird and hard to talk about. So in the reflection packages, there is a class called class. It is generic. It takes a specific generic type so that it can specify whose class it is. For instance, if we have a class called A, then a class representing A would be of the type class brackets A, where A is defined as its generic value. We can get class objects from the dot class variable that belongs to classes, or calling get class from an object. So there are two different ways to get the class. If you know the name of the class in your code, you could just say a.class. Or if you have a variable and you're curious about getting the class that that variable's type represents, then we can call getClass like we did here on our object. You and I, looking at the code, know that its type will be its class will be the B class, but as the program runs, the JVM doesn't necessarily know that. So we're going to call getClass on that object, and that should give us the class object that represents B. We could print it out and it would say class B. Then we can get the fields from it, meaning the instance variables. There are a couple of ways to get fields. There is getFields, which will return all the public fields for the current class and the public fields declared in the parent classes. Remember that private fields can't be accessed by subclasses anyway, so getFields will return us up the inheritance tree, but it will only work with the public fields from this class or the parents. And then getDeclaredFields will return all of the fields from this specific class, whether they are public or not public. So when we call getDeclaredFields here, we are getting all of the fields from B, including the private ones. We are not getting any fields from A, even though B extends A, because it's getting only the ones declared in B. And so then we can mark them accessible. So we can actually change them from in our code from being treated as private to being treated as public, essentially. This is controlled and either allowed or disallowed by the security settings when Java is run. So you can tell Java not to allow this kind of thing to happen because, of course, if you actually mark something private, it may be serious that it stay private. And so you can turn on or off the security settings to allow or disallow this sort of thing. We've marked them to be accessible, so we've basically overridden the privacy on them with our reflection here. And then we will loop over each field in that set of fields, and we will get the value from that field. F.get gets us the value for that field, and then we can print it out. And we're able to print out that there is an int number that's equal to 671 and an int year that's equal to 2012, and so on. So in just this example here, we were able to get the fields from a class based on an object of that type, and then change their access level and print out their details. Printing out F will print out the private int b.year and their actual values when we use get on those. We can also get a specific field like number to try to look up a particular field by name. There are lots of ways that we can take the actual name and try to look things up, and we'll see some more of those later. This means that we could allow users to examine details of our code or to do things like some of those libraries you may have seen that make Java programming easier for kids because they just ask, what would you like your thing to be called? And what value would you like to go in it? And things like that. We can break apart or put together classes using things that are defined at runtime. This could have been read in from command line, and we could examine fields or we could add new fields or things like that at runtime. We can set that field accessible just like we did before. We can set its value, and then we can move on and get another field. So remember that get field will only look for the public ones, but it will get it from parent classes. So here we can change the number, the year, and the course, even though those are declared across two different classes. And we can change the values for them so that once we've done this, it would be CS 745 from 2013. We can also examine what the superclasses are of the class that we are working with here. C was the one that we got from a B object, so C would be the class for B. Its superclass is A. So we've essentially been able to do the same as O.course equals CS, except this line wouldn't work unless O was a variable of type B. So we've been able to get what the class was, and we've been able to pick up the particular field, that it was the course field, and to set a value for it without a variable of that specific type. And it's worth noting that getSuperClass returns null for object or interfaces or primitive types. Yes, there are class objects for primitive types. It's a bit strange. So here we're messing with the class of our reflection class. So we take the reflection class, we call .class on it, And then we're able to do things like to request a new instance of it. This will call the default constructor for the reflection class. So it's the same as saying new reflection with empty parentheses. Then we can loop through the different methods that come from that reflection class. And we can invoke each of those methods. So we get the method that's double, called DBL. We provide the name. Again, this could have been provided at command line or by some simplified, learn how to program Java tool or something like that we were writing. We can get that particular method, and then we can invoke it using the string parameter CS, which would give us the doubled CS. So here's an example of where we're really playing fast and loose with things, that we're calling invoke, and we're providing it a parameter, and that parameter had better be of the right type for this. If it's not of the right type, or I haven't given the right number of parameters, then I get exceptions here. So I'm invoking methods with information there, with parameters there, and it could go very wrong if I give the wrong type of parameter. Whereas a compiler would have checked that for me if I were actually calling, something double with an integer instead of a string. It would give me a compile time error there, potentially. Or call toString on it to automatically convert, various things like that. But there would be things that would help smooth it out for me or let me know early that an error was about to happen. Here we're in a bit wilder of a situation where we're allowed to invoke it and just cross our fingers and hope that we got the things right in terms of the number of parameters or types of parameters. We can use get constructors or get declared constructors to access the different constructors that are not just the default one with no parameters. It is worth also paying attention that the way that exceptions are handled is different between class.newInstance and constructor.newInstance. They both have the same method name, but they're two different structures inside of the reflection package, and you should pay attention to which one you're using so that you know and handle the correct exceptions for each of those. So we also can do some interesting stuff in terms of the structure and inheritance inside of our programs when we're doing reflection. Let's say we have an interface I, and we have some class that implements that interface. And that means that it should have a getName method of its own. And it may have other methods of its own as well, like a constructor that the interface would not have. So we can get the class of this some class thing. We could have done it the way we did above, where we create an instance of some class and then we get the class from it. Lots of different ways. One other way that we're going to see here is that I can actually ask for a class by name. So again, a user could provide this at command line, or we could get this from some other place that would ask us for the class by a particular name. We could check if a class exists and try to get it by that particular name. So here we ask class.forName some class, so that looks up some class in our class loader. And then we can say if I is assignable from C. What this is essentially asking is, if I had a variable of type I, could I put a C in it? Could I put a some class in it? And I could say I thing equals new some class, because some class implements I. So it's asking if I is a superclass of C, is another way of thinking of this. But it does it with this question of being assignable. Could I assign a C into an I variable? Yes, I could. That means I is a superclass of C. So we can then narrow down our types. We can make a new class variable that is stating that our class here, CI, is something that extends I. And what that's going to let me do is to then treat things as i's, just like I could do with an I variable that holds an instance of some class. And then I say C as subclass, which means basically sort of cast it or restrict it as a subclass of I. So take that some class, and now we know that it's a subclass of I, so take it and cast it so that it's stored as something that we have confirmed is a subclass of I. That will allow me to treat it as an I, like creating an I variable and storing a new instance of that CSI. I would not be able to do this with C. I would not be able to say C.newInstance on this side of the equation because I haven't confirmed that C is a subclass of I at the time that I created C. And so I have to restrict it a little bit to be able to do this, or the compiler would yell at me and say that it doesn't actually know if this thing here can be stored in an I variable. So this kind of allows me to go from a less restricted state where I don't know much about some class and then learn that some class could be stored as an I variable and then do that later on down here. And then I print out the name from it just to call that getName method that I know is guaranteed for all I objects. The getConstructor call will throw a no such method exception if the constructor is not found. So if it's an abstract class and doesn't have a constructor, then you would get this exception here. A few more little notes here. You don't have to call setAccessible for public fields. They're already accessible, so you don't have to change it to be accessible. Or if it would be accessible in the space that you're in, similarly, we don't have to set it as being accessible. It may, however, be rejected by the security manager I mentioned before. You can run Java with a security manager that will cause it to reject when people try to change the accessibility through reflection of pieces of your code. And the class.forName, as I mentioned before, uses a class loader. The default class loader is the one that looks in your class path. So whatever your class path is defined as, for instance, if JUnit is included in your class path, like we do in this class, then you could load up JUnit classes using the class loader. You can also create a class loader that loads things over a network using URLs so that you could provide the URLs of some online classes that someone has put on a site or on a server or has tried to transfer to you, and you could then load those up by calling class.forName. So this is a way that you can load remote classes over a network or over other resources to be able to run code that didn't actually exist when your code was compiled, and load in those classes and use them inside of your application. This has got all sorts of security risks, and you really want to think about trusted sources and things like this, but it allows you to add new functionality external to your application and work with it. Most of those methods from class will throw, as I mentioned before, a variety of exceptions, which means that in assignments, when you're asked to do reflection in those assignments, you should catch those. If I give you a class name that will not be found by your class loader, you will get exceptions for that, and you should catch those exceptions, and all sorts of similar things like that. I mentioned before that we were really playing fast and loose with the arguments for the method that we were invoking. So we could be a little more secure and a little more explicit in making sure that we got the right method by using getMethod and specifying the types of the arguments that would go to it. Here we have several main methods. They won't all be run by Java like a main method, only this one would, but we've got several methods called main, one with no arguments, one with a string and any object, one with 2 integers, and then the regular one with the array of strings for arguments. We can get the class C from this class that we're in, and then we create a variable for methods, and we can get the various main methods. When we call getMethod with no arguments, we get, or no other arguments other than the name main, we get the version of main with no parameters. And when we call get method with main and then the class for string and the class for object, we'll get the one that has a string and an object as its parameters. And we can even do the primitive int.class or integer.type for the wrapper class. Integer.type will return us the primitive type that integer class wraps. You cannot, however, use integer.class because that's a different class than the primitive type int.class. It gets a little confusing, just like those wrapper classes can tend to be a little confusing. You will get a no such method exception if you try to use the integer class when you really mean the int primitive type. And then similarly, we can get the standard main method from inside of itself using the get method call with main and the string array class. Even arrays have their own class that we could access. So as you can see, reflection allows us to dig deeper into objects and types that we already have, or it allows us to load in and to access objects and types that didn't exist to us previously, such as loading in things from a URL or from remote resources. So reflection can be very powerful, but also can be very dangerous. We're accessing things that were intended to be private. We are changing things about a class that maybe weren't supposed to be changed by its designer. We are loading in code that we may not have written. We may not have verified the source. And so security and thoughtfulness are really important in this, but they allow us to add functionality to our programs, either by delving deeper into our classes and our objects, or by loading in more functionality from outside.